Good morning, everybody there. So in the last class, we had seen ADC interfacing. And you have understood the program also. In today's class, let us see digital to analog converter, DAC. The digital to analog converter is a device which is used to convert a digital pulse into an analog signal. Analog to digital converter was converting an analog input to digital quantity, whereas the digital to analog converter is doing the reverse. It is converting the digital pulses into analog signals. There are two types of the DAC. They are binary weighted digital to analog converter and R to 2R ladder. The most commonly used DAC is DAC 0800, which is a R to 2R method, since it can achieve much higher degree precision. The very first criteria for deciding the performance of the digital to analog converter is its resolution. What is resolution? It is the function of number of binary inputs. That is, the number of data inputs decides the resolution of the digital to analog converter, since the number of analog output level is equal to the power of n, where n is the number of data inputs. Therefore, an 8-input DAC, such as DAC 0808, provides 256 discrete voltage or current pulses of the output. That is, you give digital input. Suppose if you give digital 8-bit input, how many number of discrete levels of analog pulses you are getting? 2 power 8, 256 levels of discrete voltage or current levels would be got. So digital to analog converter is used to convert digital pulses into analog signals. There are two types of the digital to analog converters. One is binary weighted DAC, other one is R to 2R, resistor ladder network. Resistor ladder network, where DAC 0800 is a family which is based on register ladder method. R to 2R, register ladder method, it is called as. It is normally used because it can achieve higher degrees of precision. What do you mean by precision? That is, the first criteria to decide the precision is resolution. What is resolution? Resolution is the function of number of inputs, digital inputs you can give. How many bits of binary inputs which you can give? You can give, suppose if you can give n-bit digital input, suppose if you can give n-bit digital input, you can get 2 power n levels of discrete outputs. Suppose if you can give 8-bit input, then you can get 256 levels of discrete current or voltage levels using DAC 0808. So DAC 0800 in digital inputs are converted into current pulses. You can just remember. DAC 0800 family converts digital inputs to current output, I out. By connecting a resistor to the I out pin, we can convert the result to voltage. I told you R to 2R ladder. In the sense, DAC output is a current. You are correcting that I out. That is the current output of the DAC. If you connect to a resistor ladder network, then you can get the voltage. The total current provided the I out pin is a function of binary numbers D0 to D7 out inputs and the reference current IREF. That is, I out is equal to IREF into D7 by 2 D6 by 4, D5 by 8, D4 by 16, D3 by 32, D2 by 64, D1 by 128, D0 by 256, where D0 is the LSB and D7 is the MSB. IREF is the input current and it must be applied. The IREF current is generally 2 milliamps. Connect the output pin to a resistor and convert this to a current to voltage. So this is how it is done. So IREF current output is isolated by connecting an op-amp 74M1 with RF is equal to 5 kilo ohms like this. You can just see here. So VREF you are giving plus 5 volts. You are connecting to RF of 2.5 K. So 5 volts divided by 2.5 K gives you 2 milliamps IREF current here. IREF current. And this is the I out pin which you are connecting to a 741 op amp with the 5K output. So that I out is connected to V out. Voltage you are connecting. So here P1.0 to P1.7 of 8051 is given to 5 to 12 inputs. That is D7 is given to MSB, D0 is given to LSB. So that this is the digital input which is provided by the microcontroller. This is how microcontroller is 8051 is interfaced to DAC 0800. So you can see V out on CRO. You can generate any waveform. You can write any program for generating a square wave, triangular wave, sine wave. So this is an experiment actually in your 8051 microcontroller lab. So your concepts you should know very clearly. So have you understood this? So I am asking you in the chat box. Have you understood? If you are having any doubt, you can ask. So have you understood? So 8-bit digital input, you are connecting from port 1 and DAC 0800 gives you current as the output. Digital analog signal, it is analog current you are getting. That you would convert it into a voltage by connecting a resistor. But that resistor is connected through an op-amp. Connect the output pin to a resistor and convert this current to, in real life, they can cause inaccuracy since the input resistance of the load where it is connected will also affect the output voltage. So what I am telling is here, if you directly connect this to a resistor, you will be having some input load. It may also affect. That is why to isolate that load, the load, you are connecting that to an op amp such as 741 with RF is equal to 5 kilo ohms. That's how you are connecting it. So I out, the I out current. So it is not IREF, it is a print mistake. It should be I out. So I out current output is isolated by connecting an op amp such as 741 with the R out is equal to 5 kilo ohms. With the R out is equal to 5 kilo ohms for the feedback resistor. This one. So how you are getting the I out? This is using this formula. It's very easy formula it is. Don't know whether you have understood that or not. So this formula, I don't know whether you have understood it. You can just even find it. So I out is equal to I ref into D7. So this is a flower bracket here. This is you have to understand very, very clearly that formula. So D7 by 2 LSB to MSB. So D7 by 2 plus D6 by 2 power 2 plus D5 by 2 power 3 plus D4 by 2 power 4 plus D3 by 2 power 5 plus D2 by 2 power 6 plus D1 by 2 power 7 plus D0 by 2 power 8. Suppose if you are converting the data 1001, 0101, so you have to see IREF is 2 milliamps. So D1 is 1 here, it is 1 by 2 plus 0 plus 0, D5 is 0 plus D4 is 1. So it is 1 by 16 plus D3 is 0, D2 is 1 by 64 plus 0 plus 1 divided by 256. So this you can compute. So this will be your output current. So it is 2 milliamps is IREF multiplied by it is 0.5. So this is 1 by 16 is how much? So mostly it is 0.09375 maybe. 1 by 64 is how much? You can just see that. And how what is the total? You can just find out. So it is 1 by 16 is 0.0625. So this is 0.0625 plus 1 by 64, 0.015625 plus 1 by 256. It is 0.00390.625. So plus 0.15625 plus 0.0625 plus 0.5. Multiplied by 2. It is 10 milliamps. So approximately you are going to get 10.44 milliamps. So this you are multiplying with 5K resistor. So you are going to get, so it is, you are multiplying by a 5K resistor. So you are going to get about 52 volts. So for the digital input 95H. So your binary pattern is this, no? This is your binary pattern. You are going to get 52 volts as the analog output, approximately. This is how it is done. So this formula I have explained you using an example. So this formula I am speaking. So in the output you can just see, this is I out, you are multiplying it by 5K. So V out is equal to I out into this R out. So this is the digital to analog converter part. You know how much you are appreciating, because there is no feedback. So 1 or 2, yes, I will get, that's all. That is our fate here. No feedback at all, whether you understood, not. Interest is shown. Okay. So next, write a program to generate square wave using DAC 0800 interface to 8051 microcontroller. Simple it is. So digital output is FF, that you are moving to P1, you are calling a delay. Then you are moving 00, you are calling a delay. That's repeating it. So delay is generated using timer. Timer 0 in mode 2. So T modular. So period of the square wave is 0.2 seconds approximately. That is why TH0 you are loading it as 5. Start the timer. Wait until TF0 is equal to 1 here only. Once TF0 is equal to 1, clear the timer, clear TF0 and return. So this particular delay program would generate a square wave of period 0.2 seconds. That is, one pulse width is 0.1 second actually. So P1 high pulse 0.1 second. Once again it is submitting 00. Once again low pulse. So this particular program will generate a square wave of 0.2 seconds. So the count 5 indicates that the counter counts from 5 to 255. That is why TH0 you have to load it as -5. Actually you have to load it as -5. -5 you have to load. That means from the count 5 indicates it counts from 5 to 255. Hence the delay introduced will be 256 minus 5 into 1.085 microsecond. Total it is 272.33 microsecond for each high and low pulse. So T is equal to 272.33 into 2, which is 544.66 milliseconds. Sorry, 544.66 microsecond. So the frequency will be 1 by T. So it is 1.3 kilohertz. So here there is a print mistake. It's not 0.2 seconds. It is 544 microsecond. So this you have to understand very clearly. So the frequency of the square wave is about 2 kilohertz. That is 1.83 kilohertz. So this program in the theory also we have seen it. Generating a square wave using the timer. That you have seen it already. So the note also very clearly, the count 5 indicates that the counter counts from 5 to 255. Hence the delay is 256 minus 5 into 1.085 microsecond. So that we have discussed why it is 1.085. So 1.085 is nothing but 926 kilohertz. So 11.06059.2 megahertz is divided by 12. When it is divided by 12, you are going to get 926.3 kilohertz. So one pulse width will be 1 over 926.3 into 10 power 3, which will be about 1.085 microseconds. That is one machine cycle. That is one clock pulse actually. So 256 minus 5 into, that is 251 into 1.085 microsecond gives you 272.33 microseconds for each one pulse, high as well as low. So you are going to get the period as 544.666 microseconds. So this completes the digital to analog converter. So what is the gist here? Digital to analog converter converts the digital input to analog pulses. The two types of the DACs are R2 binary weighted DAC and R2 2R ladder or resistor ladder network. So DAC 0800 is a family which uses resistor ladder network, whose output depends upon how many bits of digital input you are giving. Suppose if you are giving an n bit digital input, 2 power n is the output. And the output will be in terms of the current. So the converted to by connecting a resistor to the IO output. We converted it to voltage. So here the reference current will be 2 milliamps. And you are connecting the output pin to a op-amp with a resistor of 5K. And so your output current can be got using this formula. And the digital output is fed through port 1 in this example. Port 1. So this is a program to generate a square wave using DAC. So have you understood the program? So have you understood the concept? So I'm asking you, have you understood the concept? So last article is stepper motor interfacing. Stepper motor interfacing. So if you just see the syllabus, of 8051, we are here actually. We are in the last part. So we have completed LCD, ADC and DAC. And the last article remaining is stepper motor. Last article remaining is stepper motor. A stepper motor is widely used device that translates electrical pulses into mechanical movement. So what are the applications of stepper motor? It is normally used in disk drives, dot matrix printers, robotics. This is used for position control. So how actually a stepper motor is made up of? Next question. How actually a stepper motor is made up of? Stepper motor is has a permanent magnet called as rotor, also called as a shaft. You can just see here. This is square boxes, whatever you are seeing here. This is a shaft. It's normally called as a rotor. And it is surrounded by a stator. The most common stepper motors have 4 stator windings that are paired with a center tapped common. So this type of the stepper motor is normally called as 4-phase stepper motor. The center tap allows a change of current direction in each 2 coils when a winding is grounded, thereby resulting in a polarity change of the stator. Notice that while a conventional motor shaft runs freely, the stepper motor shaft moves fixed repeatable increment which allows one to move it to a precise position. So this repeatable fixed movement is possible as a result of basic magnetic theory, where poles of the same polarity repels and opposite polarity attract. So the direction of rotation is dictated by the stator poles determined by the current sent through the wire coils. So as the direction of current is changed, the polarity is also changed, causing the reverse motion of the motor, rotor. So there are several widely used stepper sequences which has a different degree of precision. So this is the diagram. So normal 4-step sequence where you can just see. So there are 4 shafts actually. It's A, B, C and D, to which there will be a winding. It's normally called as the stator. So this is the normal 4-step sequence where 2 windings are energized. Winding A and winding D is energized. Next, winding A and winding B. Next, winding B and winding C. Next, winding D, C and D. It's just a rotation, that's all. It's just a 1-bit circular right rotation. Half-step sequence. Half-step. In half-step, first 2 windings. In the next iteration 1. So next 2, next 1. So that alternate you go. So you can get 8 step. So this is wave where only 1 winding is energized. So these are about 3 types. One is normal 4-step, half-step 8, and another one is wave step. So stepper motor is a device which translates electrical signals into mechanical movement. Then you should know the applications of the stepper motor. Applications are disk drives, dot matrix printers, robotics, etc. So every stepper motor is a permanent magnet called as rotor. It's also called as a shaft, which is surrounded by the stator. So the most common stepper motors have 4 stator windings that are paired with a center tapped common. The most common stepper motors have 4 stator windings that are paired with a center tapped common. So this type of the stepper motor is commonly called as 4-phase stepper motor. The center tap allows the change of the current direction in each of the 2 coils when a winding is grounded, thereby resulting in the polarity change of the state. If you see it in conventional motor, it rotates freely, where the stepper motor rotates in fixed repeatable steps, which allows one to move to a precise position. The repeatable fixed movement is possible as a result of basic magnetic theory, where poles of the same polarity repels and opposite polarity attract. So the direction of rotation is always dictated by the stator poles, which is determined by the currents which is sent through the wire. As the direction of current is changed, polarity is also changed, causing the reverse motion of the rotor. So the various step sequences I have told you. One is normal 4-step is nothing but you are energizing 2 windings with the circular right shift rotation. Half step is once you energize 2 windings, next you energize 1 winding. Wave step is at an instant you energize only 1 winding. This is called as wave step. Step angle. How much movement is associated with a single step? So this depends upon internal construction of the rotor motor. In particularly number of teeth on the stator and the rotor. The step angle, how much movement is done, that depends upon the number of teeth present in stator and the rotor. The step angle is the minimum degree of rotation as a single step. So various motors have the following step angles. The total number of the steps needed to rotate one complete rotation is 360 degree divided by 1.8 degrees. That is a single step 1 point. So totally it is 200 steps. So if the step angle is 1.8, you are going to get 200 steps for resolution. If the step angle is 0.72, 500 steps. If it is 2, if it is 180, if it is 2.5, it is 144, if it is 5, it is 72, if it is 7.5, it is 48, it is 15, if it is 24. So RPM is revolutions per minute. So steps per second is equal to RPM into steps per revolution divided by 60. So the relationship between RPM, steps per rotation, and steps per second is as follows. So steps per second is RPM into steps per revolution divided by 60. A practical stepper motor will always have 1.8 degree step angle and a 50 tooth in its rotor. So there are 8 main poles of the stator, each having a 5 tooth in pole face. So the step angle is given by A is equal to 360 N into K, where N is the number of rotor tooth, K is the excitation sequence factor. So all of you are answer your attendance. All of you please answer your attendance. So next is motor speed. The motor speed is measured by steps per second, is a function of switch rate. The motor speed is measured in steps per second, which is a function of switching rate. Holding torque. The following definition is the holding. With the motor shaft at standstill or 0 RPM, the amount of torque from an external source required to break away the shaft from its holding position. So the amount of torque which is required from an external source, which is required to break away the shaft, that is from the standstill position into rotation at the beginning. How much torque is required from an external source? So this is called as holding torque. So this is measured by rated voltage and the current applied to the motor. So the unit is ounce inch or kg centimeter. So that is the unit of holding torque. So these are the applications of the stepper motor. There are several areas of where the stepper motors like instrumentation, computer peripherals, machine tool drives, etc. Tiny stepper motor is used in quartz analog watches for driving the second, minute, and hours hands. So these motors operate directly with the button cells used in each electronic watches. So bigger stepper motors are used for driving the hands of slave clocks on railway platforms, bus stations, offices, factories, etc. Computer peripherals for an important area for card readers, punchers, paper tape readers, teleprinters, dotmatic printers. So normally they use stepper motor. They also find the applications in very old floppy disk, hard disk, etc. The main application is numerical control systems for machine tools. So normally we use even in robotics, the stepper motor. So in your final year project work, normally you use stepper motor for designing any line follower robot, or wherever there is a movement which is in steps, you are going to use the stepper motor. So in the medical field also it is used, in the medical fields, in X-ray machines. So the latest that I told you, industrial robots are normally used for by the stepper motors. So next is stepper motor interfacing to 8051. Here also you are using port 1, P1.0, 1.1, 1.2, 1.3 to drive the 4 stator windings, which is like this. You are driving it for supplying the current which is required for the coils. You are using a stepper motor driver also, which is nothing but ULN 2003, which is a stepper motor driver. So here you are using one power supply for the motor and the other for the motor and ULN 2003 and another for 805. You are using separate power supply. So this is the power supply you are using for motor and ULN. Another power supply you are using it for microcontroller. So this you can see it in the next class.